Bonding the neutral is proper only at the transformer, isolating the neutral bar and the circuit breaker panel from the panel itself. This ensures the neutral remains connected to the grounding system at a single point, preventing neutral currents from flowing through the panel enclosure or other equipment. The rigid metal conduit, or RMC, between the transformer case and circuit breaker panel serves as the equipment grounding conductor, or EG, for the downstream equipment. It provides a low impedance path for fault currents to return to the source, ensuring the safe operation of the transformer and connected equipment. A transformer with a secondary winding electrically isolated from the primary winding is considered a separately derived system, or SDS. Under certain conditions, a transformer may be treated as an SDS in an industrial plant. Firstly, if the transformer is rated 50 kV or less. Secondly, if the transformer is used to supply a specific load or equipment, such as a motor control center or uninterruptible power supply system. Thirdly, if the transformer is isolated from the primary system by grounding the secondary neutral. The National Electrical Code, or NEC, defines an SDS as a system in which the electrical supply is derived from a source independent of the supply from any other system, containing transformer-based sources of electrical supply, isolated from earth such that the voltage between any conductor and earth does not exceed 300 volts. In the scenario, the transformer meets the criteria for an SDS since it has a secondary voltage less than 300 volts, specifically 120 volts, and is grounded at the secondary neutral. Therefore, it can be treated as an SDS in the industrial plant. Local electrical codes and regulations may have additional requirements or variations on these guidelines. It is always advisable to consult with local authorities and qualified electricians for proper installation and compliance. In summary, the key aspects to consider include firstly, the single-point bonding of the neutral at the transformer, secondly, the RMC serving as the equipment grounding conductor, and thirdly, the applicability of the separately derived system classification based on the transformer's characteristics and usage. The importance of adhering to local electrical codes and consulting with qualified professionals cannot be overstated, ensuring both safety and compliance. Transformers are critical components in electrical systems, facilitating voltage transformation to suit various load requirements. They operate based on the principle of electromagnetic induction, where alternating current in the primary winding induces a voltage in the secondary winding. The turns ratio between the primary and secondary windings determines the voltage transformation ratio. Proper installation and grounding of transformers are essential for safety and reliable operation. Grounding ensures that fault currents have a low impedance path back to the source, minimizing the risk of electric shock and equipment damage. The National Electrical Code, or NEC, provides comprehensive guidelines for the installation and grounding of transformers, covering aspects such as conductor sizing, overcurrent protection, and bonding requirements. Separately derived systems, or SDSs, introduce unique considerations for grounding and bonding. An SDS is an electrical system where the power is derived from a source independent of the main power supply, typically a transformer, generator, or battery system. When an SDS is present, a separate grounding electrode system must be established to ensure proper fault current flow and minimize voltage potential between grounded metal parts. The grounding electrode system for an SDS typically consists of a grounding electrode conductor connected to a grounding electrode, such as a ground rod, metal water pipe, or building steel. The size of the grounding electrode conductor is determined by the size of the derived phase conductors, as specified in NEC Table 250.66. In addition to the grounding electrode system, bonding jumpers are required to connect the SDS equipment grounding conductors to the grounding electrode conductor. Bonding jumpers ensure that all metal parts within the SDS are at the same ground potential, reducing the risk of electric shock. The size of the bonding jumpers is determined by the size of the derived phase conductors, as specified in NEC Table 250.102. Overcurrent protection is another critical aspect of transformer installation. Overcurrent devices, such as circuit breakers or fuses, are used to protect the transformer and connected equipment from overloads and short circuits. The size of the overcurrent devices must be selected based on the transformer's rated primary and secondary currents, as well as the ampacity of the conductors connected to the transformer. NEC Article 450 provides detailed requirements for transformer overcurrent protection, including the maximum allowable overcurrent device ratings and the location of the overcurrent devices. Proper conductor sizing is also essential for transformer installations. Conductors must be sized to carry the rated current of the transformer, taking into account ampacity dating factors for ambient temperature and conductor bundling. NEC Table 310.15 provides ampacity ratings for various conductor types and sizes, while NEC Article 310 provides guidelines for ampacity dating. In addition to conductor sizing, the type of conductor insulation must be selected based on the operating voltage and environmental conditions. Conductors used in wet or corrosive environments must have appropriate insulation to prevent insulation breakdown and electrical faults. Furthermore, the physical protection of conductors is important to prevent mechanical damage and ensure long-term reliability. Conductors should be installed in conduit, cable trays, or other protective enclosures to shield them from physical damage. The selection of the appropriate wiring method depends on the specific application and environmental conditions. Wiring methods commonly used for transformer installations include rigid metal conduit, intermediate metal conduit, electrical metallic tubing, and flexible metal conduit. Each wiring method has its own advantages and disadvantages in terms of cost, installation difficulty, and environmental suitability. Regular inspection and maintenance are crucial for ensuring the continued safe and reliable operation of transformers. Inspection should include visual checks for signs of damage, overheating, or corrosion, as well as electrical tests to verify insulation resistance and winding integrity. Maintenance activities may include cleaning, tightening connections, and replacing worn or damaged components. A comprehensive maintenance program can help to identify and address potential problems before they lead to equipment failure. In addition to the technical aspects of transformer installation and maintenance, it is important to consider safety practices. Working with electrical equipment can be dangerous, and it is essential to follow proper safety procedures to prevent electric shock and other injuries. Safety practices include energizing equipment before working on it, using appropriate personal protective equipment, and following lockout-tagout procedures. Lockout-tagout procedures ensure that equipment is properly de-energized and cannot be accidentally re-energized while work is being performed. Training and qualification are also essential for personnel who work on electrical equipment. Employees should receive training on the hazards of electricity, proper safety procedures, and the operation and maintenance of electrical equipment. Only qualified personnel should be allowed to perform electrical work, ensuring that they have the knowledge and skills necessary to perform the work safely and effectively. The grounding electrode conductor should be sized according to NEC Table 250.66, based on the size of the derived and grounded conductors. The grounding electrode conductor must be securely connected to the grounding electrode using approved methods such as exothermic welding, listed connectors, or bolted connections. The bonding jumper between the separately derived system equipment grounding conductors and the grounding electrode conductor should be sized according to NEC Table 250.102, based on the size of the derived and grounded conductors. The bonding jumper must be installed in a manner that provides a low impedance path for fault current. The neutral conductor of the separately derived system should be connected to the grounding electrode conductor at a single point, typically at the transformer or generator. This connection ensures that the neutral conductor is at ground potential, minimizing the risk of voltage potential between the neutral conductor and ground. The equipment grounding conductors for the separately derived system should be connected to the grounding busbar in the panel board or equipment being served. This connection provides a low impedance path for fault current to return to the source, ensuring the safe operation of the equipment. The panel board or equipment being served by the separately derived system should be marked to indicate that it is part of a separately derived system. This marking helps to ensure that personnel are aware of the unique grounding requirements for the system. In addition to the general requirements for separately derived systems, there are specific requirements for different types of systems. For example, separately derived systems used to supply sensitive electronic equipment may require additional grounding and bonding measures to minimize electrical noise and interference. These measures may include the use of isolated ground receptacles, shielded cables, and surge protective devices. Separately derived systems used in healthcare facilities have additional requirements to ensure patient safety. These requirements include the use of isolated power systems, which provide a higher level of protection against electrical shock. Isolated power systems use a special transformer to isolate the power supply from ground, minimizing the risk of leakage current. The installation and maintenance of separately derived systems require specialized knowledge and skills. It is important to consult with qualified electrical professionals to ensure that the system is installed and maintained in accordance with applicable codes and standards. Improperly installed or maintained separately derived systems can pose a significant risk of electrical shock, fire, and equipment damage. Therefore, it is essential to prioritize safety and compliance when working with these systems. In summary, separately derived systems are an important part of many electrical systems, providing a reliable source of power for critical loads. However, they also require careful attention to grounding, bonding, and overcurrent protection to ensure safe and reliable operation. By following the requirements of the NEC and consulting with qualified electrical professionals, it is possible to install and maintain separately derived systems that meet the needs of the application and provide a safe and reliable source of power. The transformer's primary and secondary voltage and current ratings must be clearly marked on the nameplate. The transformer must be installed in a location that is accessible for inspection and maintenance. The transformer must be protected from physical damage. The transformer must be properly ventilated to prevent overheating. The transformer must be installed in accordance with all applicable codes and standards. The grounding electrode system must be installed in accordance with NEC Article 250, Part 3. The grounding electrode system must be connected to the built-in grounding electrode system if one exists. The grounding electrode conductor must be sized according to NEC Table 250.66. The bonding jumper between the separately derived system equipment grounding conductors and the grounding electrode conductor must be sized according to NEC Table 250.102. The neutral conductor of the separately derived system must be connected to the grounding electrode conductor at a single point, typically at the transformer or generator. The equipment grounding conductors for the separately derived system must be connected to the grounding busbar in the panel board or equipment being served. The panel board or equipment being served by the separately derived system must be marked to indicate that it is part of a separately derived system. In addition to these general requirements, there are specific requirements for different types of separately derived systems. For example, separately derived systems used to supply sensitive electronic equipment may require additional grounding and bonding measures to minimize electrical noise and interference. Separately derived systems used in healthcare facilities have additional requirements to ensure patient safety. The installation and maintenance of separately derived systems require specialized knowledge and skills. It is important to consult with qualified electrical professionals to ensure that the system is installed and maintained in accordance with applicable codes and standards. Improperly installed or maintained separately derived systems can pose a significant risk of electrical shock, fire, and equipment damage. Therefore, it is essential to prioritize safety and compliance when working with these systems. The separately derived system must have a grounded conductor, typically the neutral, unless specific exceptions apply, such as for certain control circuits or systems operating at less than 50 volts. The grounding electrode conductor, connecting the system's grounded conductor to the grounding electrode, must be sized according to NEC Table 250.66, based on the size of the derived and grounded conductors. The grounding electrode itself must meet the requirements of NEC Article 250, Part 3, which specifies acceptable grounding electrodes such as metal water pipes, building steel, or ground rods. The bonding jumpers connecting the equipment grounding conductors to the separately derived system's grounded conductor must be sized according to NEC Table 250.102, based on the size of the derived and grounded conductors. The location of the grounding connection for the separately derived system is critical. It must be made at the source of the separately derived system, such as the transformer or generator, and not at any point downstream. This ensures that fault current has a direct path back to the source, minimizing voltage rise on equipment grounding conductors. All metal enclosures and raceways associated with the separately derived system must be effectively bonded together and connected to the system's grounding electrode conductor. This includes metal conduit, junction boxes, and equipment enclosures. Overcurrent protection devices, such as circuit breakers or fuses, must be properly sized and installed to protect the separately derived system from overloads and short circuits. The overcurrent protection devices must be coordinated with the system's conductors and equipment to ensure selective tripping and minimize the extent of any outage. The conductors supplying the separately derived system must be sized to carry the calculated load in accordance with NEC Article 220. The conductors must also be protected from physical damage and installed in accordance with the NEC wiring methods requirements. The separately derived system must be properly identified with signage indicating that it is a separately derived system and identifying the location of the grounding connection. This helps to ensure that personnel are aware of the system's unique grounding requirements. Regular inspection and maintenance of the separately derived system are essential to ensure its continued safe and reliable operation. This includes visual inspections of grounding connections, conductor insulation, and overcurrent protection devices, as well as electrical testing to verify the integrity of the system. Any deficiencies identified during inspections or testing must be promptly corrected to prevent potential hazards. The NEC provides detailed requirements for the installation and grounding of separately derived systems, and it is essential to follow these requirements carefully to ensure the safety of personnel and property. It is also important to consult with qualified electrical professionals to ensure that the system is properly designed and installed. The secondary neutral must be bonded to ground at the transformer location. This bond establishes the reference point for the separately derived system. An equipment grounding conductor, or EG, must be run with the circuit conductors from the transformer to the panel board. This EGC provides a low impedance path for fault current to return to the source. The neutral conductor should be isolated from the panel board enclosure. This prevents neutral current from flowing through the enclosure, which can create a shock hazard. The panel board enclosure must be bonded to the EGC. This ensures that the enclosure is at the same potential as the EGC, reducing the risk of electric shock. All metallic components of the electrical system, such as conduit and junction boxes, must be bonded together. This creates a continuous, low-impedance path for fault current. The grounding electrode system for the separately derived system must meet the requirements of NEC Article 250. This includes the use of a grounding electrode conductor, or GEC, to connect the system to a grounding electrode, such as a ground rod or metal water pipe. The size of the GEC must be determined based on the size of the ungrounded conductors of the separately derived system. The overcurrent protection for the separately derived system must be sized in accordance with NEC Article 240. This includes the use of circuit breakers or fuses to protect the conductors and equipment from overloads and short circuits. The conductors for the separately derived system must be sized in accordance with NEC Article 310. This includes the use of ampacity tables to determine the appropriate conductor size based on the load and installation conditions. The separately derived system must be properly labeled to identify it as such. This helps to prevent confusion and ensures that the system is properly maintained. It is important to note that the requirements for separately derived systems can be complex. It is always best to consult with a qualified electrical professional to ensure that the system is properly installed and maintained. They can perform a thorough inspection of the system and ensure that it meets all applicable codes and standards. A properly installed and maintained separately derived system can provide a safe and reliable source of power for sensitive equipment.